There we are. Great. And yes, without further ado, we look forward to your talk, Hector.
Thank you very much, Petra. And first of all, let me thank you and Sarah for inviting me and hosting me. And I'm very glad to be here. I'm going to be talking about a field that my group founded a few years ago that we called Algorithmic Information Dynamics. And I'm going to try to focus on this talk on networks and systems, especially evolving systems. So as you may know, there are a multiplicity of complexity measures that serve different purposes. And there are so many today that it almost looks and feels like everybody has their own toy measure, and everybody comes with a new measure for their own project. So part of the talk is going to try to cover whether there's some sort of hierarchy of which complexity measures are more fundamental than others, and which ones we have basically used to provide the foundations behind what we are trying to do. So here on the screen, you are seeing an oversimplification of the description of a few popular complexity measures coming from classical probability, answering how likely some event is, for example. There's also Shannon entropy, which is kind of a measure of usually called uncertainty, but I see it more as a as a measure of diversity. We then have more sophisticated measures that are way less utilized because of arguments related to uncomputability, for example. And these are related to Kolmogorov complexity, also called algorithmic complexity, the other side of the coin, which is called algorithmic probability. And these are measures that quantify how algorithmically likely something is and how random something may be. Even more obscure measures like logical depth, thermodynamic depth, that basically measure how many number of operations or how much work is invested into an object to or an event to happen. Some others like fractal dimension quantify how rough something is, and so on. One popular one is, of course, computational time complexity, for example. So in the limit, how a function grows as a function of something else, and so on. So the interesting thing is that actually all these measures are kind of related to each other. I'm going to try to cover some of it, but this is a list of what I think are very fundamental, what I call laws of classical information and classical computation coming from, for example, Shannon entropy, but then the definitions of Kolmogorov complexity that in the next slides I'm going to cover, and algorithmic probability, which is a very, very interesting metric, and how they relate to each other in what is called the coding theorem. And as I was saying, all these metrics are in some way connected to each other. We don't know necessarily exactly which way. It is an under-researched topic. But just to give an example, objects, for example, with low Shannon entropy have obviously low Kolmogorov complexity, but the other way around doesn't apply. Not necessarily unless you have access to the probability distribution, but this is something I'm going to be talking still about. So each metric has also different degree of difficulty. So we used to use a lot of Shannon entropy-based metrics, for example. I call them friends because they are very easy to be applied, so they are computable. We don't have to think much about it. It's just a methodology that you can apply to almost every piece of data. Compression complexity is another one, and sometimes it is abused to relate it to algorithmic complexity. But we have made the case that actually it is more related to Shannon entropy, and we are going to see some examples about it precisely in the context of complex networks. But it is also computable. It's like Lemped sieve and all those kind of compression measures. I guess we have settled on them because, again, they are computable, they are very easy to be applied. And then we have a range of other measures that are that have different degrees of uncomputability and are more difficult to be applied. They are way more powerful, and that's the point that we are going to be making today. But then people and scientists don't use them much, precisely under these kind of arguments that we sometimes call them fear to uncomputability. But one of the arguments that we are going to be making, as you can see in the note below the table, is that in many areas of science, there are uncomputable things, including most of the questions that we ask about systems. And that doesn't mean that we have to avoid them only because it is difficult to estimate them or calculate them. And we believe that we can enrich these statistical measures like Shannon entropy with more sophisticated ones. So let me first start by defining what is algorithmic complexity, also called complexity or Kolmogorov-Chaitin complexity. So basically, it's the length of the shortest computer program that running on a universal computer, a digital computer, gives you back the original piece of data that you wanted to quantify the complexity on. So in this case, it could be a string, a binary string, and you want to calculate the algorithmic complexity of that string. So you are looking for the size of the shortest computer program P that running on a computer U basically produces as an output original string. And this is a definition that was given in the 60s. And just to explain it with a couple of examples, you can see here that what is called the two-Morse sequence, which is very interesting. So you start with a 0 and you binary negate the 0. So the next digit is a 1. And the next two digits is basically the negation of the first segment of the sequence. So you have now 1, 0, because the first one was 0, 1. And you keep building this sequence. So it is completely algorithmic, and it was shown to be Borel normal, which is very interesting. Basically, it means that there's no over-representation of any segment of this sequence. So all the segments of any size are equally represented in this infinite sequencing. In other words, it is maximal entropy because there's no statistical difference. This is similar with pi, at least believed in some bases, because it has been proven, I think in base 10, I think in base 2, it has been proven to be Borel normal. But again, this basically means that if you are using Shannon entropy to characterize these digits as a stream of information that is coming to you, you wouldn't be able to say anything interesting about them. Obviously, if you knew that this is pi, you know it is very low, lowest Shannon entropy, because it is completely deterministic. So this is a kind of a criticism sometimes I've got from Shannon entropy colleagues. How do you speak about Shannon entropy of pi when pi is deterministic? And that is absolutely true. But if you remember in textbooks, for example, the classical example is tossing a coin, and then you model that as a random variable. But tossing a coin is completely deterministic too, and you still apply Shannon entropy on it, because basically you don't know the outcome. You are modeling it as a random variable. Here is exactly the same. Imagine you are given the digits of pi, but you don't really know that it's pi. Can you tell anything interesting about it? And if you use all these statistical metrics, including Shannon entropy or block Shannon entropy, doesn't matter how much sophisticated you get your Shannon entropy measure, you will never say anything interesting about these sequences, even when they are absolutely interesting, right? Because pi is one of the most interesting mathematical constants in science, and there are plenty of formulas and algorithms that produce pi. And for me, this is kind of an example of what happens in science, and because you have an observer looking at something that may appear like random, but it is not. And what you want to find is the mechanistic model that produces that object to understand it and even predict the next digits. If you were looking at these digits and ask what is the next digit, you wouldn't be able to say anything about it with Shannon entropy. But if you knew the program of pi and you had it, then you could run the program and basically know exactly what is the next digit. And for me, that's the interesting part of Kolmogorov complexity. It is less about finding the shortest computer program but more about finding any computer program or set of computer programs that basically gives you a mechanistic explanation for your object. Now, how fundamental this measure actually is? Well, turns out that actually is quite fundamental because in the 60s, different mathematicians wanted to characterize the concept of randomness, and they came up with different definitions based on prediction, compressibility, and betting against the next outcome. And turns out that the three different definitions independently provided were equivalent with each other and basically characterize the same function, the Kolmogorov complexity of the string. So it is quite fundamental, and basically there's an agreement among mathematicians working on randomness that this is the mathematical definition of randomness and simplicity or complexity. So it is not just yet another complexity measure or a toy metric. So here's an example that is also going to tell us why it is uncomputable, but that doesn't mean that we cannot estimate it. So we have this string with 0 that looks like 0, 1, 0, 1, and so on. Basically, you can come up with a short computer program that reproduces the infinite sequence. So we already know that this sequence is of low Kolmogorov complexity. The other way around is more difficult. If you have a string that looks random and you don't find a short computer program, you can never tell whether it has a short computer program or not. And that's the piece that basically gives you the uncomputability, that you never can tell with certainty that something that looks random is actually random. But you can always keep trying and find that. That's basically what we do in science. Something looks random, how the stars are on the sky, for example. At the beginning, it looked random, but then we keep trying at finding a model that explains how objects on the sky move. And it turns out that we found these beautiful models around gravitation that can explain not only the sky, but also why we are stuck on the floor and on Earth and so on. So for me, all this science and algorithmic complexity are very much related in that we want to find the causal models behind data. And it is less interesting about finding the shortest. The shortest is just a theoretical tool to prove theorems about this metric. So in some way, we have a measure to rule them all, because you can see that, if you go to through these papers, that Kolmogorov complexity is very fundamental and basically is an upper or lower bound to different other complexity metrics. And that is deeply related to pretty much everything else. So we won't have time to go through all of this, but this is just to say that it is of quite fundamental nature. We have used this metric, here is just an example, also behind what is called logical depth, introduced by Charles Bennett in the 80s, which uses Kolmogorov complexity. And the idea is basically to look at the compression time. Because Kolmogorov complexity, you can see it as a compression algorithm, right? You are looking for short models explaining your data. So it's kind of a compression method. But notice that it is not just statistical. You are not just looking for regularities, because otherwise you wouldn't be seeing anything in objects like pi or the tumor sequence. You are really looking for algorithmic or recursion compressibility. So when it comes to logical depth, what you are looking at is the compression time, and it is very interesting because with Kolmogorov complexity, basically you are assigning the greatest complexity to the most random objects. And sometimes what you mean by complexity is how sophisticated it is. No? So how somewhere in the middle between simplicity and random something is. And logical depth is very interesting because if you think about the compression time, if something is random, you cannot really compress it. The decompressing rules are very simple because it's basically just a print the random object. So there's no time in decompressing a random file. Now imagine it is very simple. A very simple file would have very simple decompression rules. So it will also decompress very quickly. So basically both simple files or simple data and random data would have low logical depth. and everything else in the middle would have large complexity. So we classify all these images by different metrics, and you can see they are quite small on the screen. But what we were able to do is basically classify all these images by what intuitively actually looks like complexity. So in the first place, we have like a circuit board, for example, then a phase, then some fractal images with some noise and so on. And then you have at the very bottom things that look random or very simple. So that's a very interesting metric that is based on Kolmorov complexity, but actually allows you also to distinguish what is not completely random and not completely trivial. And compression complexity has been also been used for a couple of decades now. And there's a landmark paper from Cilibrasi and Vitani, for example, on classifying genomic sequences and reconstructing a phylogenetic tree that you can see on the screen, which is very interesting. But a criticism I've made of this paper is actually they were not really preaching to biology, in particular molecular biology, because we know that we can basically just count the GC content in genomic sequences to reconstruct most of the phylogenetic trees. And that's because genomes that have about the same GC content are related to each other because of evolutionary reasons. In other words, you can just reproduce this tree not using compression algorithms, but Shannon entropy. And that was to our point, that compression complexity is really more related to compression, to Shannon entropy, sorry. And you can see it also in this graph. This is a typical Bernoulli graph. I have another example later, where you plot the distribution of Shannon entropy values over different genomic sequences with different GC fractions. You have curves that look very much related when you do the compression versus Shannon entropy. And when you use one of our methods, the distribution starts looking much more different. And you will see another example later on. So this is a very interesting example of what happens with Shannon entropy, which is not as powerful as Kolmorov complexity. So this is a completely recursive network we came up with. And you basically start with one node, and then you keep adding nodes depending on how many edges to the original nodes you had in the first place. So if you look at this small piece, for example, you have that the node with label 1 only has one edge. And then node with label 2 has two edges. And node with label 3 has only two, but in the next step, then you complete it because you need three edges for the node that has three as label. So it is basically on the label based the number of edges. If you keep going, and this was completely on purpose, it turns out that the node degree distribution is just the natural number sequence. So 1, 2, 3, 4, 5, and so on. So when you try to characterize this network by looking at the degree distribution, it looks like maximal entropy. So you wouldn't be able to say anything interesting about this network, even when it is completely recursively constructed. But when you look at the adjacency matrix, it looks very low Shannon entropy. So basically two completely different descriptions of the same network that allow you to reconstruct that network fully have completely opposite divergent Shannon entropy measures. So that basically means that Shannon entropy is completely observer dependent, and we use it all over the place, including in neural networks for loss function and so on. So you can see how it is missing very important features that are causal, because here the main property of this network is that it is causally generated. We have a formula, which is not here, by the way, it is a very beautiful one, that generates the whole network. And yet, if you apply Shannon entropy on different descriptions, you get completely different results. And that is basically because you don't have some sort of invariance theorem as you have in Kolmorov complexity. So in Kolmorov complexity, what was proven is that you may think what happens if I measure algorithmic complexity of a string using a different computer that is running on a different program or programming language? Maybe I get different results. And you may, but actually there's a theorem that guarantees that in the limit, you get exactly the same result. And here for Shannon entropy, you don't. So obviously there are challenges because we don't know how fast we converge. And part of my research has been to show or find out empirically how fast we converge to the same values using algorithmic complexity. But at least we have that guarantee that eventually we converge to the same values. With Shannon entropy, you don't, and it is very easy to construct these kind of counter examples where you see that Shannon entropy fails at characterizing an object. So can we do better than Shannon entropy? That's one question, because obviously it's quite challenging to measure Kolmor's complexity. And we think we can, and all this is based on a beautiful concept called algorithmic probability. And to explain it, I'm going to use again the example of the mathematical constant pi. So imagine that you have a typewriter and you have a human, or also usually the example is with a monkey. So the question is whether you would reproduce the digits of pi having a monkey randomly type writing on a typewriter. And you can see that it's very difficult the longer the number of digits, right? So it's 1 over 10 because it's base 10 in this case. 1 over 10 to the number of digits that you want to get right. So that's a probability. So the probability diminishes exponentially when you place a random source trying to reproduce at random the digits of pi. So we know with classical probability that is very unlikely. But things change dramatically if instead you use a computer and the monkey is based on a keyboard where every key is basically a piece of computer program, a random piece of a computer program. Then things change dramatically because the monkey has to reproduce the program that reproduces pi, not pi itself. And because pi is low algorithmic complexity, it has a short description. So you can see how much more likely it is for a monkey on a computer to produce highly structured objects if they are using a computer program as a random input rather than just the digits themselves. And that concept is called algorithmic probability. It's basically replacing the typewriter with a computer program. So now you can define algorithm probability as the size of the computer program instead of the size of the number of digits that you want to get right. And that is completely related to algorithmic complexity because that size of the computer program is precisely the definition of Kolmor's complexity. The shorter, the closest you get to algorithmic complexity. And this is a completely fundamental metric that came up, that was introduced by Ray Solomonoff, who was in this very famous AI conference in Dartmouth in the US, where the concept of AI was coined for the first time. I think that was in the 50s. And you can see him in this picture next to people like Shannon himself, John McCarthy, Marvin Minsky, and so on. And all these people and all the scientists later on have agreed that actually this is the optimal method for inference. So when you have an object, basically what you are looking for is to try to come up with the algorithmic probability of that object. And it is very fundamental to AI as well. So there's a lot I could say about this, but let me move to how actually we exploited it to try to come up with this new metric to characterize objects. So what we have here on the screen is a flow diagram of computer programs where we start from the smallest to the largest one to try to explain the small pieces of data. And then the computer programs behind basically are the models that can explain the data. And we have the examples that I've given before. So we have the sequence of, for example, natural numbers or the natural numbers in binary. So any of the examples I've given before, like the 2-more sequence or pi in any base, we will be able to eventually find the computer program that reproduces it. Obviously, it may take a long time. So what we did is basically to break down the problem into small pieces. So we don't require the algorithm to reproduce the whole sequence, but the small parts. And if one can test it, and basically you come up with these beautiful models for which we can even come up with the state space diagram, which is completely different to Shannon entropy. Shannon entropy is just descriptive, but not prescriptive. So with this computer program, basically you can run and verify if the next prediction corresponds to the observation and so on. So from running this, basically we count how many computer programs are able to explain small pieces of data, and we have a counter. So the more times we find a model that can explain the data, the more likely it has high algorithmic probability. So in other words, it is causally generated. And you may ask, is it giving you any edge? And actually it is. So I can give you, for example, two examples of short binary strings that have very high, almost maximal Shannon entropy, but they are generated with small computer programs. So this is exactly what we were talking about, that we are starting to find those cases in which Shannon entropy would tell you that something is random, but actually it is not, because it is very highly likely that it was reproduced by a short model, a causal model, shorter than the data itself. So this is almost like giving you another dimension to Shannon entropy, where you can find those cases in which you can explain something causally, even when it may look random, which is very common in the real world. That's what happens all the time. As I put the example of how planets or stars are distributed on the sky. So you may also think, oh, but maybe this is too theoretical. This only applies to Turing machines and computer programs of certain type. Well, it doesn't. So we made also the experiment of using all sorts of computer models. And remember, Turing universality basically means that you can write down a function as a computer program, and a function can be anything, including every piece of mathematics known to us and to scientists. So pretty much everything that we do, including, for example, modeling the weather with simulations on a digital computer, is basically reproducible by a computer program. So it is not like a niche of computer programs that can explain data. It's really covering everything. So when you look at different computational models with different levels of computation, some of them are not even Turing universal, you can still explain simplicity bias with algorithmic probability, and this is what this is showing. So as you may remember, there's this Chomsky hierarchy that gives you different computational levels of power. Basically, we wanted to see if we could explain part of the simplicity bias in the data that generates these random computer programs in different models with algorithmic probability. And it turns out that it is a very likely hypothesis, no, that you can still explain a good portion of that bias. So this is for me why Kolmorov complexity or algorithmic complexity is quite fundamental, because usually what we have is some sort of deterministic system, like tossing a coin, and then we have an observer that doesn't have access to kind of the source code. And the output may look completely random, but actually it is not. So we can have either misled observers with some examples that may have some statistical regularity, or something that looks random but is actually pseudo-random, because there's a computer program that is able to generate the output of an object. And basically the question about Kolmorov complexity is to try to find these computer programs to explain the observation. So we apply this to inverse problems. So let's say that we have, these are called cellular automata for those that are not familiar with. These are computer programs that have a visual representation. It's a discrete dynamical system that evolves from top to bottom. So you have a rule at the beginning and it evolves. Some of them can be very simple, but actually even with simple rules and simple initial configurations, you can start reproducing a lot of complexity. So one question was whether we could reproduce these dynamical systems if we scrambled them. So you can scramble every row and then ask our algorithm to try to come up with the most likely configuration or causal model and the computer program that explain this or the computer program. And we could, and you can see here the reconstruction. It is not exactly the same. Sometimes we would get exactly the same, but I'm actually plotting the one that had the same value, but it was not the same, just to be fair. So this is the worst kind of prediction. And you can see the similarities between these systems. It is quite precise. And then actually you can keep running the system and then ask the method to come up with a timestamp of each row, because one thing is to reconstruct the original configuration of the computer program, and another one is actually to give you the time step of every one. And this is what we came up with. And some of these errors, because you can see that it is not fully reconstructed the original computer program, we know why where they are coming from. But still, you can see that it does a relatively good job. Even this one that is completely reversed has some sort of trend. So this is a completely blind experiment with a typical inverse problem. So we started also applying to different things that we knew couldn't be settled before, and whether our algorithms would contribute to anything. So there's a very famous experiment with ants introduced in the 60s. Actually, it was kind of controversial, but regardless of whether it was controversial or not, the hypothesis was that ants would take longer to communicate the instructions of where food is on a maze, controlling by everything else like pheromones and those kind of things, because they keep replacing like the paths. And they measured the time that ants would, the foragers ants would take to come back and communicate the location of the food to the other ants. And the hypothesis was that the more complex the instructions, the longer the time they would take. But they couldn't quantify it. So we applied our metrics to this experiment, and we got precisely their hypothesis. We confirmed the hypothesis. Whereas if you apply Shannon entropy, even in their best versions like block entropy and those kind of things, basically you get just a flat line. We also did it in a nice PLOS computational biology paper that we published a number of years ago on human subjects. So we had 5 tasks to assess the perception or generation of randomness from people from different ages, all the way from almost babies to elder people. And they were asked to reproduce, for example, what would be a random sequence of tossing a coin, or whether this configuration of this array would look random to them, or this one. And then again, we apply Shannon entropy on our measurements. And if you apply Shannon entropy, you get like flat lines. And if you apply ours, you get these very nice curves that basically correspond to most of the curves in cognitive science, where you see a decline starting from the 20s, 30s, all the way to the 60s, and also an increase of capabilities from where you are very young to around 25 years old. So this is at generating and perceiving randomness. So that was also very interesting. And then this is the part where we introduced algorithmic information dynamics, because what we are doing is combining all these methods with perturbation analysis. And here's the basic idea. So you have a piece of data. In this case, the original one was just a string, an infinite sequence of ones. And the original computer program to reproduce that piece of data was this one, because you are just reproducing ones. But what happens if you modify a single digit? Then the model in software space grows in size. So basically, every perturbation you do at the level of the data has an impact on the model. and the set of the models, because I remember we not only have one, but we have like a set of models, and we can explore and study how the model changes when we perturb the data. And that turned out to be a very interesting concept, and also allows you to characterize data, because if you have like random data, if you perturb it randomly as well, then the computer program, the model, doesn't change much because it was already random. So it was kind of a print, the original object. So whatever you change, the model remains the same. But if the data is causally generated, then perturbations to that data has greater impact into the original model. So turns out to be very interesting, and you can apply it to all sorts of objects, including networks. So for networks, we have these two extremes for algorithmic complexity of a network. Either something is very simple because it has a very short description. So for example, a complete graph is basically connect every node to every other node. And that's basically the computer program. It is very short, so you don't have to do anything. But see how that would change if you remove a single edge. Then the computer program actually dramatically changes, because you have to explain that perturbation. Everything else was very simple, very short, but suddenly you remove a random edge. You have to explain which exact random edge you have removed. On the other extreme, you have a completely random graph. And then if you have a random graph, the computer program is quite long, as long as the network itself, because basically you have to specify every starting and ending point of every edge. So everything complex and interesting for us is in the middle. And again, in a random network, if you remove a random edge, your original computer program doesn't change anything. And then you have a complex one. Actually, you can kind of remove uh, edges and nodes in a smarter way to either move the original computer program to simplicity or randomness. So you can quantify the contribution of every element, nodes or edges, and that's what we call signatures. And it could be a node signature or an edge signature on whether perturbing, for example, removing an edge or a node changes much, and by how much, the original computer program or model. We use also this for what we call algorithmic deconvolution. And an example is, for example, two sequences that are concatenated one after the other. One is very simple and the other one is random. And you put them together through the algorithm and basically start making cuts as a form of perturbation, and look at the segments. And then you see up to what point you can explain that segment with the same computer program. And then when it starts diverging, and that may be another program. So that's why we call it the convolution, because different parts of a sequence that has different generating mechanisms can be identified and divided. And we can even come up with a computer program that explained the first part, because the second one was actually random. So we have something that is able to deconvolve an object. This is another very interesting example. You may remember the irreversible message that was sent to space with what we believe is kind of a diagram that extraterrestrial life may understand in some way. But there are so many basic questions. I mean, even if they get the original one may challenge whether they would understand anything. But one first thing is whether they would even know that it was a two-dimensional image, because this was sent as a stream of bits with a Arecibo radio telescope. So they would actually need to take the one-dimensional object and figure out that it was actually meant to be a picture. So one question we asked is the original message actually encoding its geometry? And it turns out that, very interesting, yes, it is. And that is completely mathematical. So when you start playing with different configurations, it is the original meaning which has the lowest column of complexity. And then the closer you get, also the lowest point you have. So in other words, non-random data can encode its own geometry. And that was very interesting. And we used it also for things like alignment for biological purposes. So by doing all this perturbation analysis on networks, we also took like genetic regulatory networks and thought whether we would be picking up any signal. So what we call negative or positive nodes or edges that basically move the original computer program explaining a network towards randomness or simplicity would be actually picking any biologically significant feature in a genetic regulatory network. And we use 3 different gene enrichment databases that you can see on the screen: Gene Ontology, KEGG, ECHO, Psych. And in the three of them, and obviously we did all the controlled experiments, also doing perturbation at random or perturbation following Shannon entropy, and we couldn't come up with significant, statistically significant groups using the same enrichment analysis platforms. But when using algorithmic information dynamics, we could actually categorize nodes that have the same effect when you remove them with some biological meaning. And turns out that, for example, one group of genes that are related to removing nodes that move the original model to randomness or simplicity are related to homeostatic processes, for example, which kind of makes sense a posteriori, but this is something we still have to validate, because those nodes that you remove and basically send your original model to randomness are kind of suggesting that you are removing something fundamental for the system to keep working. And that's kind of related to homeostatic processes. But then you also have specialized processes for the other example, for the nodes that when you remove, send the original model to simplicity and so on. So that was very interesting. And we applied it also to a known signaling network related to oncology. And it turns out that the pathway that is known to be more prone to mutations producing cancer was also the most fragile in our framework. So that when you actually touch, moves the original model, which is an explanation for the whole network, that has greater impact. And we published that one in Open Science by the Royal Society. So I think I'm going to stop there for any questions. We published a book by precisely Cambridge University Press a couple of years ago when I was at Cambridge. And also, I think last year we published this other book by Springer on methods and applications of algorithmic complexity. Thank you very much.